Okay, I want to take a quick look at the solutions for the 4.4 practice number 2. I'll talk more about this when I'm actually at school, but I want to just talk to you very briefly about what it looks like. We're going to talk about solving larger linear systems. Well, let's just look at what a linear equation with 3 variables represents. When we deal with bigger linear equations with involving 3 or more variables, we almost always are going to want to write them in a standard form. So like if we wrote a linear equation in 2 variables, say x and y in standard form, we know what that is. Standard form for linear equation, remember, is ax plus by equals c, where a, b, and c are integers, and we typically like a to be positive. Okay, so if we did this for a linear system involving 3 variables, x, y, and z, it would look like ax plus by plus cz equals d, for example. Or once again, a, b, c, and d would be integers this time. And what does that look like? Well, where a linear equation in 2 variables represents a line, a linear equation in 3 variables represents a plane. And so if we look at a system of 3 linear equations in 3 variables, and we want to find the solutions to that linear system, and here's, real quick, here's an example of one. Notice I've got the variables x, y, and z, and one of the variables or more could be missing from any one of these equations, but in the system as a whole, you can see that there are 3 different variables and 3 different equations, right? So we call that a 3 by 3 linear system. Remember that we have to have at least as many equations as we have unknowns. We need at least 3 equations if we're going to have 3 variables. Okay, so algebraically, when we're trying to solve a linear system like this, instead of looking for the ordered pair, we're looking for the ordered triple. We're looking for the values of x, y, and z that satisfy each of these 3 equations, that make each of the 3 equations true. Okay, so that's, algebraically, it's not a big stretch compared to what we did with a 2 by 2 linear system. So our answer is going to be in the form x, y, z, where x, y, and z will be the coordinates in 3-dimensional space. So instead of just having an x and a y, x and y axes, now we've got a z axis coming out of the board. So it's 3-dimensional. Okay, so, oops. There we go. Okay, so what would those 3 linear equations look like? Well, they're all going to be planes. What are the different ways that 3 planes could interact? The 3 planes, and by the way, this is of course how planes are infinite. You can't draw something infinite, so we usually just draw a piece of each plane. We could have 3 parallel planes that never intersect, and so that would be an example of no solutions. There'd be no places where those 3 planes intersect. Same thing here, right? We've got 2 planes are intersecting at a time, but 2 of the planes are parallel and never intersect. So once again, there's no place where, there's no point that will simultaneously be on all 3 planes. And the same thing is true here. We've got 3 planes. Each plane intersects 2 other planes, but never in the same place. So here's so like for example, these 2 planes intersect in a line, and these 2 planes intersect in a line, but the lines are all parallel. So once again, there is no point in this picture right here where the point is simultaneously on all 3 planes. Okay, well, if we move down, here's an example of 3 planes that do intersect in a single point. Okay, and so there would be one unique solution here with the values of x, y, and z corresponding to that point. And then here's an example where all 3 planes intersect in the same line, and so this would be an example where there would be infinitely many solutions to this system. This one is a little tricky, and I'm not going to put any of those on I'll let the cat out of the bag. I guess I gave it away. I'm not going to put any of those on the problem set, nor will I put any of those on the test. We'll talk more about those later in the year. It's a yeah, well, I'll talk more about it later. It's a little more complicated because we have to come up with the equation of that line in 3 space, which is a little strange. So we'll deal with that later. I'll never test you on it, but I'll talk to you about it later. So let's try this then. How does this work? In order to solve a linear system in a 3x3 linear system, we must write each of the linear equations in standard form, which just means that the variables are in the same order. Typically we go alphabetical order, so the x term first, then the y term, then the z term, and on the other side of the equation is the constant. And what we're going to do is we're going to build what's called a matrix. This is a great trick. This is going to be a pretty easy assignment because really all you're going to do is just practice this little trick, but it's a very useful one. It's useful in mathematics, it's useful in science. You'll do this in Mr. Cooper's honors chemistry class, you'll do it in my honors physics class. We're going to build what's called a coefficient matrix. So we're just going to take, as long as they're written, all 3 equations are written in standard form, so the x term first, y term, then z term, constant on the other side, we're just going to input into the matrix only the values of the coefficients, and that's a 1 there, isn't it? And the constants. So the matrix would look like this. The first row of the matrix would just look like 3, -2, 5, -45. The second row would just look like 5, -5, 1. There's the coefficient of z there is 1. And then -54. Third row would look like 3, 1, -2, -2. And here's where we get to use our calculator to do all the heavy lifting for us. So there's our matrix. On the calculator, notice there is a dedicated matrix button. If you hit second and then the inverse button, it takes us to the matrix screen. There are 3 menus. The names menu, which is where I always call it where you grab matrices to use in equations, for example. We're not going to do any of that stuff necessarily. The math menu allows you to do all kinds of fancy matrix arithmetic and algebra with the matrices. There's only one thing we're going to use in there. And then the edit menu is probably the most important one, at least initially. That's where we build the matrix. So we're going to build matrix A to correspond to this coefficient matrix that we built from this 3x3 linear system. Okay, and so I'm going to hit enter, and then first thing it wants are the dimensions of the matrix. Well, when we talk about the dimensions of a matrix, the first dimension is always the number of rows, and the next dimension is the number of columns. So this one has 3 rows and 4 columns. So this would be a 3 by 4 matrix. Okay, and then all we're going to do is just populate the matrix with the coefficients. So I can just go 3, and if I hit enter, it jumps me along that row. -2, enter, 5, enter, -45, enter. Then it automatically jumps me down to the next row. So the next row starts with a 5, -5, 1, and -54. And then finally the bottom row, 3, 1, -2, -2. Okay, so there's my matrix. Now all I've got to do, I'm just going to get out of there, I'll hit quit, and then I'm going to go back to the matrix screen, and then I'm going to go over to the math menu. And I'm going to go down, it's easier actually to go up. What I want to do here is this is really, technically RREF stands for reduced row echelon form. So I'm going to put this matrix into reduced row echelon form. So I'm going to choose B, RREF, and then I want to do that to the matrix A that I built. So I'm going to go second matrix, I'm going to choose A, and I'm going to close the parentheses and hit enter. And look what it does. Okay, it gives me the answer. Now let's take this matrix and let's transform this into a linear system. So think what that's saying. If my matrix looks like it's going to go, the first row is 1x plus 0y plus 0z equals -5, right? Well, what is that really saying? That first row is really just saying that x equals -5. Okay, the next row, the middle row, look what this is saying up here. It's saying 0. Remember, the first column represents the x terms, second column represents the y terms, third column represents the z terms, fourth column represents the constants. So look at that. Oh, I got small. Oh, what did I do? Okay, I'm back. Got it fixed. So the second row, look what this is saying. This is saying 0x plus 1y plus 0z equals 5. So the second row is telling us y equals 5. And the third row is telling us 0x plus 0y plus 1z equals -4. So in other words, z equals -4. So that just becomes the ordered triple, -5, 5, -4. Okay. So what we look for then, we know that we're going to get a single solution if we end up with the first 3 columns and 3 rows have a diagonal with only 1s in it and all the rest are 0s. And then the fourth column just represents the values of each of those variables. Okay. So okay, so then we would just input this as the ordered triple 5, and really all I've got to do is just look. If I get that distinctive look right there where I've got the first square part of the matrix, the first 3 by 3 part of the matrix looks, we call that an identity matrix, and I'll, later on you'll learn more about this stuff. But if it looks like that, top left to bottom right are all 1s, everything else is 0s, then that means that the fourth column just represents the variables in order. So that's going to be -5 is the x value, 5 is the y value, and -4 is the z value. And there it is. Okay, so real quick, all right, this is a big system. That's okay. This would take a really long time to do if you didn't have a calculator with matrix capabilities. But we do, so this isn't that big a deal. Right, so we've got to turn this into, how many variables are there? Well, v, w, x, y, z. There are 5 variables and 5 unknowns. And so we need to turn this into a coefficient matrix, first of all. Okay, so there's my 5 by 5 matrix. Like I said, let's turn that into a coefficient matrix. And so, what's that look like? Well, the first row looks like 2v. We have to, and notice these are all written in standard form. The variables go in alphabetical order from left to right, and the constants are on the other side. So 2 is the value of v, 3 is the value of w. No, that's going to have to make that bigger, aren't I? That's not going to work. Let me do this. Okay, so in our 5 by 5 matrix, there's going to be, or 5 by 6 actually, right? We've got 5 variables plus the constants. Oh, darn it, I cut off the constant. Oh my gosh, I'm struggling. So I'm going to have a 5 by 6 matrix, 5 rows for each of the 5 equations, and 6 columns. 5 columns for the coefficients of the variables, and a 6th column for the constants. So if I organize this, then I'm going to have kind of my V coefficients. You don't have to do this, but I'll do it once so you can see what's going on. My W coefficients, my X coefficients, my coefficients of Y, my coefficients of Z, and then my constant on the other side. So the first row then looks like 2V plus 3W plus 2X plus 5Y minus 5Z equals 2. Next row, negative 1V plus 2W minus 3, oops, there are no X's. Look, there are no X's, so that means what's the coefficient of X? It's 0. So I got to put a 0 in the X column for row 2. Plus minus 3Y plus 4Z equals 11. Next row, 1V minus 2W plus 1X plus 1Y plus 4Z equals 14. Next one, we get negative 2V plus 3W. There's no X term, so we get a 0 coefficient of X. Minus 1 is the coefficient of Y. There's no Z, so the 0 is the coefficient of Z. It equals 7. And then finally, the last one, negative 4, negative 2, negative 3. There's no Y term, so the coefficient of Y is 0. The coefficient of Z is 1. It equals negative 2. So there's my matrix. All I've got to do is put that into the calculator and then just store that as matrix A and then do reduced row echelon form for matrix A. So I'll do one of these just so you can see a big matrix. Why does it keep doing that? Okay, so let's go to the matrix menu, go over to edit, and we want this one, instead of being a 3 by 4, we want it to be a 5 by 6. Okay, so 2, enter, 3, enter, 2, enter, 5, enter, negative 5, enter, 2, enter. Jumps me down to row 2, negative 1, 2. Notice I'm just writing over the top of the last one. That's fine to do. 0, negative 3, 4, 11, row 3, 1, negative 2, 1, 1, 4, 14, row 4, okay, and then the last row, everything's in. Okay, so now there's my matrix A, so I'll just go to the matrix menu. I'll scoot over to math, go up to reduced row echelon form. It's easier to go up from the bottom. Oh, you know what I did? Darn it. I can't believe I did this. That's bad. Okay, I forgot to quit. You got to get out of So you got to quit, get completely out of the matrix. Then you go into the matrix screen, go over to math, go up to RREF, and I grab matrix A. And if I put that in reduced row echelon form, that's what I get. So notice this looks like what it's supposed to look like. Oh, I can't take a picture of that, darn it. Okay, but notice if you look at the screen here, if you look at the first 5 rows and 5 columns, I get that same upper left to bottom right are ones, everything else is a 0. So think what that's saying. It tells me that the first variable, which was a v equals -3, 1 times w equals 1, 1 times x equals 5, etc. So these are the values in order of the variables v, w, x, y, and z. So the solution to this one is going to be an ordered, what would I call that, a quintuple. Oops, and there's supposed to be a v in there too. Oops, so I'll have to fix that. One little minor error. So it should be of the form ordered, not a triple, it should be an ordered quintuple of the form v, w, x, y, z. I'll fix that. So then we'll put it in as -3, comma 1, comma 5, comma 2, comma 3. Okay, there it is. And that is, trust me, that is a really slick little trick, because otherwise that problem would have taken a while to do. Okay. All right, so moving on. Oh, I want to show you an example. Okay. Yeah, let's look at this one. Okay, so let's put this right into the calculator. How about? We'll just put this coefficient matrix right in. Okay, so we'll go matrix, edit, and this is going to be a 3x3 matrix, or 3x4 matrix, right? It's a 3x3 system. So matrix A, 3, enter 4. So 3x4, and then what are my coefficients in order? So -2, first row is -2, -1, 3, 49. Next row is -3, -5, -3, -16. Last row 6, 10, 6, 80. Okay, and we'll quit. We'll go matrix, math menu, RREF for matrix A, close the parentheses, and notice what we get here. Okay, this is not like the other ones were, right? This looks different. We end up with the first 3x3 portion of the matrix does not look like a diagonal upper left to bottom right of ones and the rest zeros. So this is not a single solution. If you look at the bottom row in this equation, look what it's, or in this matrix, look what it means. 0x plus 0y plus 0z equals 1. So what's that telling us? That's impossible, right? That's like saying 0 equals 1, which never happens. And so what do you suppose the answer to this problem is? It would be no solutions, because that is never true. And so NS. Okay, so that's how you spot a case where there are no solutions, when you don't get that telltale diagonal of ones and zeros for the first square part of the matrix, and the bottom row is all going to be zeros except the last constant will be a 1. So it'll be a string of zeros and then a 1. And that always tells us it's no solution. Okay. last thing I want to show you here is how you can fit a quadratic equation in general form. Okay, so first of all, what is a quadratic equation in general form? A quadratic equation in general form is just like this. It looks like ax squared plus bx plus c equals 0. Okay, where a, b, and c are just some real numbers. Okay, so how are we going to do that? Well, in this case, they're giving us 3 solutions to the quadratic equation, right? They're telling us that if we look at the graph, the parabola goes through the 3 points, negative 115, negative 353, and negative 230. Okay, think what that implies. That means that if I choose an x value of negative 1, the corresponding y value would be 15, for example. And so, for example, this, if we're going to fit this to, once again, the general form for the parabola, the quadratic equation is just ax squared plus bx plus c equals, y equals ax squared plus bx plus c, sorry. That's general form. Y equals ax squared plus bx plus c. Okay, so that's one way to write that parabola. We've done it. We used a different method earlier. There's a bunch of different ways you can represent a parabola. This is just a different way of doing it, where a, b, and c are real numbers. Okay, so what does this first point tell us then? First point tells us that if x is negative 1, y is 15. So that would tell us, if we plug these values into our general form, it tells us that we end up with 15 equals a times negative 1 squared plus b times negative 1 plus c. Or in other words, why don't we put the y on the other side, and we end up getting the equation negative 1 squared is just 1, so a negative 1 times b, so a minus b plus c equals, and then we'll put the y value on the other side. Okay, what about this point? Well, once again, if we plug that into our general form equation, when x is negative 3, y is 53. So that's telling us that 53 equals a times negative 3 squared plus b times negative 3 plus c. So once again, if we just collect those terms, we'll push the 53 over to the right side. Negative 3 squared is 9, so we get 9 times a, or 9a, minus 3b plus c equals 53. And then finally, the point negative 230, if we plug that into the general form, gives us the result, a y value of 30 equals a times the x value of negative 2 squared plus b times negative 2 plus c. And so that gives us, use the color, that gives us 4a minus 2b plus c equals, and we'll push the 30 over to the other side, flip those around, and we get equals 30. So that looks an awful lot like a 3 by 3 linear system, right? In the unknowns, or the variables a, b, and c, right? So we could just, if we want to know what the coefficients of x squared, x, and the constant are in our quadratic function in general form, then all we got to do is just put this 3 by 3 linear system into the calculator and find its solution. Okay, so matrix A is going to be a 3 by 4, First row, what are the coefficients? Coefficient of A is 1. Coefficient of B is -1. Coefficient of C is 1. And the constant is 15. Next row. Coefficient of A is 9. Coefficient of B is -3. Coefficient of C is 1. Constant is 53. Third row. Coefficient of A is 4. Coefficient of B is -2. Coefficient of C is 1. Constant is 30. So we quit. We go to the matrix screen, math menu, RREF of matrix A. So look what that tells us. It tells us that A is 4, B is -3, C is 8. And so if I want to write this function out, then I just get the function f of x equals 4x, because ax squared, right? So 4x squared plus, minus 3x plus 8. That's what f of x is equal to. Okay? And then, so there's just another example of one like that, where you're actually graphed it, so you can see the 3 points on the parabola. And then the bonus one, I'll show you how to do this one too, or the challenge question. I want exact answers. Okay, you can do this though. If you put in fractions into your, how did this work? Oh, I know what it was. There's a trick on this. Okay, so with this one, we've got these 3 points. Remember, this was the tricky one. They want you to provide, it's really not a big deal. They want you to provide exact values of A, B, and C, because we're trying to fit this quadratic function to the general form y equals ax squared plus bx plus c. So let's just take each of those solutions, values of x and y, they're going to work in this equation. So first point is going to give us ax squared plus bx plus c. What's that going to give us? Well, a times x squared, x is 2, right? So 2 squared times a plus b times x times 2 plus c equals y. And y is equal in that first point to 0. Okay, so next point, this one. So this is going to give us a times x squared, x in this case is 4, times 4 squared plus b times x plus c equals the y value, which is 1. Remember, we're just going to put the y on the other side. And then finally, we got the last point, a times x squared plus b times x plus c equals y. And so if I simplify that, I just end up, the red equation becomes 4a plus 2b plus c equals 0. The green equation becomes 16a plus 4b plus c equals 1. And the purple equation becomes, 25a plus 5b plus c equals -5. And so we're going to take that linear system into the calculator. Oops. And let the calculator solve it. Okay, so I've already done this. There's matrix A, right? I already put it in. So I want to put that into reduced row echelon form. So I go second matrix, math menu, RREF for matrix A. And there's what I get. So X equals this decimal, or I mean, sorry, A equals that decimal, B equals that decimal, C equals that decimal. But those aren't exact, are they? At least two of those are not exact. And so I've got to, I want to turn those into fractions. Well, there's a great little trick for this. If I go to the math menu and I just convert to fraction, which is the first option, I can take my previous answer and convert that to fractions, and look what it does. It tells me that A is equal to negative 13/6, B is equal to 27/2, and C is equal to negative 55/3. And so if I want to write the function then, the function is just going to look like f of x equals negative negative 13/6. Because remember, what I'm doing here is I'm answering the question, what is f of x equal? Ax squared, so there's a x squared plus b is 27/2 times that, whoops, times x plus c, which is just 55/3. And those are exact values of the coefficients, and so that is the exact value of the function that fits this parabola that goes through those 3 points. F of x equals, I'm just filling in the blank, f of x equals, f of x or y equals that. Okay, we got it. All right, that's that.